Hello again, Scott Arthur here, back with the latest instalment of D21UD. After a lot of careful thought, I've decided to call this class 3B. Okay, in the last class we spoke about how we could estimate the amount of rainfall reaching a catchment surface and some of the considerations around that. In this class, what I want to do is speak about how we can think about how the rainfall converts to runoff and how the volumes and rates involved can be estimated. So really what we're thinking here is about the transformation of the rainfall hyetograph into a runoff hydrograph, and that involves two steps really. So the reduction of the volume due to losses and routing of the overland flow. Now, I've just prepared this little sketch in the top right here about routing. So even if we assume there's no losses due to infiltration, etc., what we would expect is for the rainfall profile as indicated. Pen here. We expect the peak to be lowered and the base to be lengthened out as it travels, as it's attenuated as it travels over the catchment surface. So that's really just what the routing component's about. So, the bottom of the slide, losses can be considered as being of two types. Initial, so that's losses that happen at the start of the rainfall event and then stop. And then continual, so that's losses that continue throughout the rainfall event. So for both those loss types, the clue is in the name. So of course we know that the amount of runoff from a catchment surface changes substantially once it's developed, and the nature of that development also has an impact. So it's not just development that's an issue, it's about how the catchment's developed. And there's a handy chart at the bottom left there which shows you an idealised difference between before and after development. So after development we expect the peak flows to be higher and occur sooner, putting more stress on the watercourse. Okay, so in a natural catchment there's not only infiltration but there's uptake by plants, and the catchment surface is rougher, so all these things mean that the volume and rate of runoff is reduced when compared to a developed catchment. So the type of development is important. So this is a Sightline industrial estate which is a mile or so away from the Edinburgh campus. So there is some green space here, but there's lots of car parks, there's lots of large roofs. Over here, sorry, over to the left, we've got the Tesco, etc., and all the car parking space there. So big car parks, big roof areas, lots of paved surfaces means there's lots of runoff. And because this is an industrial estate, even though it's not heavy industry, we would expect there to be some pollutants associated with that runoff, and so they have to be managed as well. This is in Edinburgh. It's much more suburban setting, near where I live. And what you can see here is there's more open green space, there's more gardens, and what that means is that when the rain falls in areas like this, there's lots of opportunities for it to be infiltrated directly into the ground surface. This is central Edinburgh, and in a lot of ways central Edinburgh is quite an unusual scenario because there is still quite a lot of green space there, which just means there's lots of opportunities for rainfall to be infiltrated. This is down in Leith. Keep hearing that Leith is one of the most densely populated places in Europe, and certainly in this picture, particularly towards the right of it, you can see there's not much green space, there's just lots of paved surfaces. So again, that means there's more runoff which has to be managed. But Edinburgh as a whole is quite a green city, in part because of all the golf courses. I think there's 27 or something in and around Edinburgh. Lots of parks, large suburban areas. We don't really have much in the way of really high density living, which in general I think is a good thing. This is Cairo, which is a slightly different scenario, much more dense urban environment. New York, I was in New York 2 years ago, and you struggle to find a park just to sit down and have a bit of rest. Of course, just outside this picture, well, just outside the top of the picture, this picture is Central Park, but you know, outside that, there's not really that much going on in terms of green space. So quite a high density urban environment. And this is an area of Mumbai, which is, by common consensus, is one of the most high density living areas on the planet. And again, not much green space there, not much opportunities for rainfall to fall directly on sort of natural surface. So all these different urban scenarios present different challenges to urban drainage because of the varying rates of runoff. So in highly urbanised areas, initial losses tend to be less important and may often be neglected. In more suburban areas, their influence is more important. So here we're talking about interception and wetting losses. So this consists of the collection and retention only for the initial period of the rainfall event of water. So the example in the picture here top right is rain falling on a leaf, and it does take some initial rainfall to wet the leaf before it starts to drip off the leaf, it fall onto the grass, and before it infiltrates. So all these things help delay water entering the drainage system. We also have depression storage. So this is where the uneven surfaces in urban areas can be used to collect water, like in the picture, the bottom right here. This varies based on surface type, surface slope, because obviously a sloping surface, if the surfaces are even, there's less areas where the water can collect, and rainfall return period. High intensity events mean that the depression storage doesn't fill because the water splashes out. So we can estimate depression storage using this equation. So it's a depth of depression storage across the catchment based on K and surface slope. So K is some factor which defines the catchment surface. So it's relatively straightforward. So evapotranspiration. So this is the sum of evaporation and plant transpiration from the Earth's land and ocean surface to the atmosphere. Evaporation accounts for the movement of water to the air from sources such as the soil, the canopy, interception, and water bodies. So in the UK, by and large, this is viewed as being negligible in most circumstances because it's around 3 millimetres of rainfall per day. So obviously over a year that amounts up to something that's quite significant. But for urban systems, when you look at the duration of the rainfall event, we're typically looking at minutes or hours we're concerned about. The fact that you're losing 3 millimetres of that per day due to evapotranspiration isn't something to lose too much sleep about. So where losses are concerned, infiltration represents the movement of rainwater through the ground surface and into voids within the soil. So the reason I start that by saying where losses are concerned is, remember at the start of this course we spoke about infiltration, where the water moves from the groundwater into the pipe. So I know it's the same word, but it's a completely different process. And what I find is that students quite often confuse these two processes because the same word is used to describe them. So when you come across a word, it's quite important when you think about the context of it. Okay, little tip there in case it comes up in the exam. I'm not saying it will. The infiltration capacity of the soil is the rate at which the water can infiltrate it. This is dependent on soil type, structure, compaction, initial moisture content, surface cover, depth of water above the ground level. So the issue here, so different soil types, so typically sandy, gravelly soils have high infiltration rates, and where you have clay soils, your infiltration rates are quite low. Where we know the soil conditions, we can use what's called the Horton equation to estimate infiltration rate. If we know the infiltration rate at the start, the final infiltration rate or capacity of the soil, and a decay constant. So using this equation, we can generate these kinds of curves for typical soils. And what this shows is what you expect. So whilst we're talking about continuing losses here, what you see is for all soil types, at the start of the rainfall event, the infiltration rate is relatively high, and as the rainfall event proceeds, the infiltration rate reduces until it reaches a point where it's saturated. So you could argue that to the right of that vertical line I've just shown there is where the soil is saturated. So what's happening here is the rain is falling, the soil's getting wet, it's getting wetter, and eventually it reaches a point where it really just can't accept any more, or easily accept any more flow. So the infiltration rate then begins to ease off. So it makes absolute sense. So continuing losses. So as the name implies, continuing losses are sustained throughout the rainfall event. These are always important in urban catchments, particularly those with large open spaces. Commonly they can be represented using the constant proportional loss model. So here it's the effective rainfall intensity I is equal to the net rainfall intensity multiplied by some runoff coefficient. Now, so as you would expect, for a highly urbanised catchment, your runoff coefficient is going to be trending towards 1, whereas for a really green, undeveloped catchment, it's going to be trending towards 0. Unlikely to get hit 0, but it's going to be heading that way. So runoff coefficient is dependent on land use, rainfall characteristics, history. Typically, in the UK, this will vary between 0.7 to 0.95 for impervious surfaces. So there's some examples here on the table on the right, and what you see is what I said earlier. So woodlands with sandy soil, your runoff coefficient's very low, whereas much more urbanised, you expect it to be a bit higher. This is really the same data but presented alongside information on the type of soil and also the slope as well, which is quite important. So this is an experiment, and this paper is on vision, which goes into this in a bit more detail. And what these people did was they set up 3 experimental plots. They've got asphalt with a tree in the middle, asphalt and grass, and what they did was they looked at the runoff from these 3 surfaces, and this is a good indicator of what impact having green systems, if you want to call them that, blue-green infrastructure on your catchment surface has. So if you look at the asphalt winter profile, we've got a runoff coefficient up over 0.6, but just having that tree in the middle more than halves the amount of runoff. But then with the grass, there's no runoff over the winter. Lower runoff coefficients in the summertime, but it's the same story. Just adding the tree, more than half the amount of runoff coming off that area, and the grass, having the grass there almost completely eliminates it. So this shows you the impact that, if you like, good urban design can have on runoff rates. So even having small pieces of green space, if the flow is directed to them without overloading them, there is a potential to reduce the amount of runoff coming from your catchment surface. and that means your network can be smaller, cheaper to both construct and operate. Win-win. So in most cases, data relating to how much runoff a catchment experiences is more important than the actual rainfall data. So what that means is that it's quite difficult to estimate the amount of rainfall following a catchment, and it's really important to do that well. But actually, the runoff process is estimating how much of that rainfall converts to runoff is often the bigger challenge. So for UK catchments, this can be done using the percentage runoff equation. So a runoff coefficient is percentage runoff divided by 100, and PR is defined using the equation through the middle there. Okay, so where PIMP is the percentage impermeable, soil is the soil index, so you're going from high infiltration rates through to low. Urban catchment wetness index, this is a measure of basically and how wet the catchment is. So here we are, it's class 3B, and we've got our first example for us to do. We've done some thinking questions, but this is a little numerical question for you to do in your own time. The solution to it is on vision before you get too stressed. So let's look at the question. For an urban catchment of average slope 1 in 200 and an estimated interception loss of 0.75 millimeters, calculate the net rainfall profile based on initial losses only of the following storm. Okay, so what we're going to do is, so we've got an intensity, we've got time, and we've got intensity there, and we've also got the K1 figure. We've got the slope, and we've got the initial losses. So the K1 figure and the slope, what does that enable us to calculate? If you remember back from a few slides ago, it enables us to calculate the depression storage. Okay, so the first stage is to do this question is to jot down the time and intensity in 2 vertical columns. Then from that I would convert the millimeters per hour to depth of rainfall per 5-minute time step. Okay, and then from that deduct the initial losses, so that's your interception losses and your depression storage. Okay, and that's part 1 of that. And then part 2, based on the profile from part 1, calculate the effective rainfall depth if 7 hectares of the 24 hectare catchment is impervious. If it has a soil index, of 0.34 and an urban catchment wetness index of 0.91. So what we're doing here is we're going to calculate the runoff coefficient, and then we're going to multiply, or we're going to use that to multiply each of the depths of rainfall from the first step. So let's look at a wee figure which explains what we're doing in both these steps. So if you like, the initial losses is the checked part of the profile. That's what we're calculating first, is this, and then we're looking at the don't know how that happened there. Then we're looking at calculating the continuing losses, which is the blue, which runs right through it. Okay, and then what we expect to have, I mean, this graph here is idealised, it's not the solution to the problem. What we expect to end up with is the green part, which is the runoff profile. So let's look at what I've done. So the first step, so here we are, section 1. I've written a little table down here with all the things that we know. So we know the interception losses, we know K1, we know the slope. Based on that, we can use this equation from the notes which we covered today to calculate depression storage at 1.5 0.414 millimetres. And if we add that to 0.75, draw a little circle around that, if we add them together, you get the total initial losses of 2.164. Okay, so don't forget that. In fact, let's let a line under that, 2.164 millimetres, so don't forget about it. Right, so up here what I've done is I've written down the time steps, then the intensity from the slide which gave us the initial data. Then all I've done is simply converted millimetres per hour to millimetres. Okay, all easy so far. Right, the tricky bit's coming ahead. It's not a difficult thing. You just have to think about it a wee bit. So this here is our rainfall profile as it hits the catchment surface. So the first thing we want to do is remove those initial losses. And our initial losses here are 2.164 millimetres. So what we're going to do is we're going to remove that from the first few time steps of this hydrograph and then recalculate it here. So like the first time step says that the rainfall depth is 0.33 millimetres. Our initial losses is 2.164. So in the first time step, 0.33 of that 2.64 is used up, and then in the second time step, 0.92 is used up, and then once we get to the third time step, we've used up all of that 2.164, and what is left is this. So there's no more initial losses, so these columns here can just be converted straight over, right? So that part here is the answer to question 1. Now question 2, question part 2 is about what we're doing here is we're going to calculate PR. So we're given total catchment area, we're given the impervious catchment area, we're given the soil index, and we're given the urban catchment index. Using these two, we can calculate the percentage impermeable. Remember, the keyword there is percentage, so it has to be in a percentage. So we calculate that. We know this. We know that. We know this. Well, there's the point there actually, and that means we can calculate PR as being 19.1%. So that's the percentage runoff. And based on that, we can calculate this column here. And then in this final column, we're just converting the runoff back to millimetres of rainfall per hour. And if we sum all this column up, we get that value there. Okay. So how we just to be clear, I'm not sure I covered that properly. To get the runoff depth, so this column here, we multiply this column by the 0.91. Okay. This chart here is just to remind us of the relationship between the urban catchment wetness index and the standard average annual rainfall. Okay, so you can use this chart if you know SAR, which is available in the Flood Estimation Handbook CD for any point in the UK. You can use that to estimate your urban catchment wetness index using this chart. So inspection shows that it's possible to obtain a PR value which exceeds 100% or is less than 0%. So both of those things are impossible, of course. Both eventualities are not viable, and so the PR value should normally be restricted to 20 to 100%. So if your PR value comes back as being less than 20, you should just round it up to 20, or over 100, round it down to 100. But look, we'll go back to our slides. To here, our PR value was actually 19.1, so if we followed those rules, we should have rounded up to 20. Law of procedure fixed PR approach has been reviewed in some detail and flaws noticed. The most basic of these is the assumption that runoff remains constant throughout the event. So we know that's not true. So as you remember the charts from the Horton equation, we had let's do R for runoff versus time, constant rainfall event. We expect high infiltration rates. No, it's infiltration, isn't it? Infiltration, I for infiltration. We expect high infiltration rates, but then it leaves off when the flow becomes saturated. Using a fixed PR right through the rainfall event assumes basically that our infiltration rate remains fixed all the way through it, which isn't very realistic. Particularly on catchments like the one you see in the picture, actually it's not very realistic because you've got quite a lot of green space there. For short events there'll be no runoff from that. As the event continues, you would expect those surfaces to become saturated, and then they may start to generate runoff onto your road surfaces in this example that you have to manage. So it's important to think these things through. So to counter these problems, a model was developed by H.R. Wallingford and what's called WRC, the Institute of Hydrology and Northwest Water, to try and remedy this. So its development was based on 19 of the 17 data sets used to develop the Wallingford procedure model. So the previous model, the fixed PR model, was based on 17 data sets, which I think were collected in the late 60s, I think. And they re-reviewed all these data sets, and they decided that 8 of them were questionable. So they removed those 8, including the only one which was collected in Scotland, if I recall correctly. And then they reanalyzed the data, and they come up with what's called the new UK runoff model. It's not so new now, it's actually quite old, but that's what it's called. And this is gaining, well, it's gained accepted levels of, so basically this model is available, and so is the fixed PR models are available. These are largely used in the sewer flow models, computer models, and by and large engineers will pick the one which works best for their catchment, and sometimes through trial and error, even though it has to be fully justified, of course. If they've got problems calibrating with one, they may switch to another to see if they can get better results. So using the UK model, the catchments are comprised 2 types of surface. Impervious, so this is subdivided into 2 further parts, that which is connected to the system and that which is considered to act as a pervious surface. The latter area is added to the pervious total. For pervious, runoff from these surfaces is estimated throughout the event and varies based on soil saturation levels. The basis of the approach is the equation below, which is recalculated for each time step. Right, so this isn't like the fixed PR model where you run the calculation once. The idea is that for each time step in your model, so if your models just say it's recalculating the flows in your pipe network every minute or every 5 minutes or so, it recalculates what the runoff coefficient would be. So what it does, and that's based on this parameter here called API, the antecedent precipitation index, which reflects the wetting drying over the past 30 days and is updated throughout the model. So what this parameter does is just say at the start of your rainfall event, it's not rained at all for the past 30 days. Quite unlikely in the UK. That is 0. But then once your rainfall event starts, 1 minute in, you've got some rainfall which can be used to adjust this equation. And so as your rainfall event progresses, that API number progresses, and that changes your runoff coefficient throughout the rainfall event. So you'd expect for your pervious surfaces to become more and more saturated and start to generate more runoff. So that was a big advance, and then 2014 came along, and people thought, well, actually, is this even working? It's better than the PR in some instances, but is it working fully? So then there's a feeling that it was overestimating runoff in extreme events. So this aspect, along with technical modelling issues which were resulting in the industry, they looked at a number of other mechanisms. So what has happened is what's called the UKWR model was proposed, and this is what you see here, a little bit more complex, certainly not for easy hand calculations. And this tries to do the same thing, but in a different way. And it was also proposed as part of the same study, is that for quite complex models, you might want to use artificial neural networks to describe how your model performs, how your network performs. So this slide is just really a summary of the 4 runoff models, so which we've really just covered. Well, we've covered the first 2 really as the same model, and we've looked at the new UK and the UKWR model. So runoff routing. So this is we're reaching the conclusion of this class. This is really the final step. So what we've done so far is in the last class we've estimated the amount of rainfall, and then what we've done in this class so far is we've talked about how we estimate the volume of initial losses and then the volume of continuing losses. So the final step is to think about how the flow profile changes. So basically the green bit that we're left with after all those losses are deducted, how that flow profile changes as it crosses the catchment surface and then enters the network. So what we expect to happen, if that blue profile is indeed the profile we end up with, is by the time it gets to the entrance to the network, we would expect it to, the peak to be lower and for the profile to be a bit longer. Okay. So there's lots of different ways of doing these calculations, and I'm not going to look at the calculations at all. But what I'm going to talk you through is probably the traditional way of doing this, and this is called the unit hydrograph method. So the unit hydrograph is a hydrograph which results from a known amount of rainfall falling on the catchment. So normally we consider this to be 10 millimeters of rainfall. The unit hydrograph shape should reflect the characteristics of the contributing catchment. There are a number of methods available to determine the unit hydrograph. These all aim to reflect how different travel times from different parts of the catchment influence the hydrograph. So the unit hydrograph concept was established in the 1930s, before I was born, as a method for estimating flows when designing drainage, flood control, hydropower and water supply projects. So here you have it. So here's your 10 millimeters of rainfall, and the assumption is it generates a runoff hydrograph which looks like this. Okay, so obviously the rainfall scale here is on a different scale to the runoff scale. Now the assumptions that is made is that if the volume of rainfall increases, all you have to do is scale up that hydrograph shape. Okay, so when you think about that, it's a little bit simplistic because it doesn't really take into account dynamic effects, but it assumes that you've got a known hydrograph shape for 10 millimeters. So if you've got 50 millimeters rainfall, all you have to do is multiply that by 1.5. Okay, so there's the 5 millimeter profile, the 10, and the 15. Time of rain. So it assumes that if you have 10 millimeters of rainfall, you get the response we've seen earlier, and then if there's no rainfall for a bit, then we get another 10 millimeters of rainfall, we get a further identical response. So we still get that unihydrograph response. So basically it's assuming there's no interaction between those two responses, either in terms of the flow interacting or the changes in infiltration, etc. during that. So a bit of a simplification there. And it assumes that where you've got 3 blocks of rainfall or more in quick succession, that we can just superimpose these together. So we've got, there's our time step 1, time step 2, time step 3. We can just add them on top of each other to get the total flow profile. Okay, so we assume the rainfall falls in blocks like this over time, but that can lead to blocky hydrographs, but to reduce the risk of that, you just reduce your time steps and you end up with smoother curves. Okay, so here we have the rainfall profile here. We've got our unit hydrograph shape. Often the unit hydrograph shape is a triangle, because if you don't have specific data for your catchment, the triangle is a reasonable assumption to make. Okay, so then for each, so we have this process called convolutions. So for each of the blue totals here, which is the rainfall depth after the losses, which is the red columns on top of them, we generate the triangle runoff hydrograph or unit hydrograph. And when we add those, in this case, 9 different triangles together, what we get is this hydrograph shape. And that process is called convolution. So the reason I don't cover the actual hand calculations for this is that, I mean, I've maybe not described it as such, but it's quite a simple process to follow, but doing it does involve quite a lot of calculations which are quite repetitive. I mean, as you can see in this step here. So if you do use a triangular runoff profile, you can fine tune it to meet your catchment needs if you know the time to peak, and that can make quite a difference. And time to peak is something that, if you've got a flow monitor in your sewer network, you know when the rainfall starts, so you've got peak rainfall, and then you can wait to see how much later the peak and runoff comes along, then that gives you your time to peak, and that can be a big help. Okay, and that's just looking at the time per peak from real data. Okay, so that's really all I want to talk about in terms of runoff routing. So we've reached the end of class 3, where we've looked at rainfall estimation in 3A and runoff estimation in 3B. So next time what we'll do is we'll look at how we can use that runoff data to think about how we can start sizing pipes in a network, which is quite exciting, hopefully. But before then, I've got some questions for you to do in your own time. You can think about these. Someone emailed me after last week's class and said, where do they submit their answers? You don't submit your answers, but if you've written something down, I don't mind you emailing it to me and I'll give you feedback on it. That's not a problem at all, but there's no compulsion to submit anything by a certain time. But I really do hope that you, in a quiet moment, you sit down and think about some of these questions about. And they're quite straightforward, but it's just about getting you to understand the concepts. So question 1. By referring to the underlying principles of the Horton infiltration model where appropriate, describe the infiltration process. So what was special about the Horton model? Remember, what was special was that it wasn't constant runoff. And remember, over time the infiltration rate changed. So think about why it changed and how it changed. Question 2. Compare how infiltration is dealt with within the Wallingford procedure PR model and the new UK runoff models. So what's the difference between the two of them? What's the weakness in the the PR model, and why was the new UK runoff model an improvement? And describe the physical process, or the processes, the physical processes involved in converting rainfall to runoff. Okay. So have a think about those questions. I'm sure that will help you prepare for the exam when it comes in the coming weeks. Okay, so that concludes class 3. If you've any questions, please get in touch. And remember, there's always space on the discussion board to ask questions. Okay, bye for now.